Hello and welcome back. We now take a closer look at how databases are organized in terms of consistency, or how we can ask ourselves, how do we make sure that the data is stored right in a database? So what do we mean by consistency? In a nutshell, or more informally, this describes how a data storage system behaves when adding, updating and deleting data. Essentially, the data storage system needs a set of rules, and if we adhere to these rules, the data storage system behaves in a predictable way. Now, why would we care? Because the data storage system should take care of it automatically, shouldn't it? As always, there are trade-offs. And this is summarized by the CAP theorem, or also called Brewster theorem. You can only guarantee 2 out of the 3. Consistency, availability, and partition tolerance. So what do we mean by this? Consistency, as we said before, every read receives the most recent write or an error. So we mean that if we write data into a storage system, we get consistent results when we want to read back from it. By availability, we mean that every request receives a non-error response, but not a guarantee for the most recent write. So for example, if we request that we read some data from a database, availability guarantees us that we immediately get a result back. However, that doesn't mean it's the most recent data we added to the database. We can also care about partition tolerance, so that means that the system continues to work despite arbitrarily many messages between the networks in the database, if the database operates in the cluster, are dropped and delayed. Now, why do we care about this? The CAP theorem says we can only get 2 out of 3. So we can have consistency and availability, but then we lose partition tolerance, or any other 2 combinations. So why do we care? We need to make a choice. For example, system availability or consistency guarantees. We can't have everything, so we need to look at our use case and our application, our research data management system, to think about what do we care more about, consistency or availability. And this is summarized in the ACID versus Bayes approach. So what does ACID mean? ACID is an abbreviation and stands for atomicity, so that means that transactions or groups of statements or requests to a database either succeed completely, so that means that we write something to the database and that is successful, or it fails completely, so there's no change in the database in all circumstances. So that means even when there's a power failure during the write, or if there are any errors, or hard disks fail, or a server crashes, the database is always in a guaranteed state. Consistency. Consistencies can only means that databases only go from one defined state to another, including all the rules and the constraints and the changes that we have. So for example, when we want to write to the database, atomicity guarantees and consistency that we can enter the data, the database is updated, and only then do we get the response, now everything is fine, we can read again. Isolation. If multiple transactions are done at the same time, the result is the same as if they were done one after the other. It may sound trivial, but it's quite not. Because if we, for example, have multiple clients, or if we write many things that update the tables or the data in the database, it's the same as if we do this in one transaction and multiple transactions at the same time, or if we do it subsequently. Here, the database guarantees that the order is resolved so that the database is always in a consistent state. And the last one is durability. Any committed transaction remains committed, even through a power failure, server crash, and so on. So that means that once we have brought the database to a new state, for example by adding data, that new states remain, even if something catastrophic fails. Opposed to ACID, we have the Bayes convention. Bayes means also eventual consistency. Bayes is also an abbreviation. It essentially means it's basically available. The database is always there in response to your request. Unlike, for example, an ACID compliance database, you can see that if we add data and we need to move carefully from one state to the next, the database can't respond in that time. Base means it's basically available. So we can read and write as much as possible. However, now we lose consistency. If we now, for example, write to the database and try to read too quickly, we may not reflect the latest write. So that means that we are in a soft state. Consistency isn't guaranteed, but we know that the database will be consistent eventually. So if the system doesn't crash for long enough after a write operation, we will reach consistency eventually, and then all reads after that will get the same answer. But that also means if the database happens to fail catastrophically in the meantime, there is no guarantee that the database is in a defined state. As a humorous remark, how do we remember acid versus base? In chemistry, a base is the opposite of acid, so this is how you can remember it. So acid versus base. Acid guarantees consistency and the data is always in a defined state. You always get the right answer. However, if you have a lot of data, ensuring all of these properties can slow the database down, so that enforcing consistency costs compute time, and that can be quite substantial for a large amount of data. This is the world of relational or traditional databases. Base, on the other hand, favors availability. The data may not be consistent or not yet be consistent when you access it, and this is essentially why NoSQL databases were developed. What do we choose? Again, there is no single right answer or magic bullet. It depends on what you need to do. What is your use case? What are your consistency needs? Often asset databases are simpler to use, guaranteed results and so on, but it also depends on your expected volume of data, the variety, velocity, the so-called 3 V's of big data. It also means how much data do you need to read and write at the same time? Do you care more about availability than consistency? So here you need to think about these big 3 V's of big data. How much data do we expect? What kind of data do we have? How quickly do we need to process the data? And how do we need to scale out? Maybe do we have hundreds or thousands of servers? It can be solved with money. So commercially, there are databases that sort of bridge the gap between asset versus base, like Google Spanner, Amazon Aurora Redshift, NuoDB and others. So they try to be as asset compliant as possible by retaining the benefits of base databases. However, of course, they're commercial databases that operate in the cloud, and you may not be able to use those. So we have 2 main paradigms, asset versus base. Asset favors consistency at the price of performance and availability, but that only really hits us for big data. So if you have multiple terabytes or petabytes in a single project, then you really need to care about that one. Base favors availability, but at the price of consistency. So it depends on your use case. What's more important to you or to your system? Is the system always responsive versus do we always want to require consistent state? It also depends to some extent on the kind of data, and maybe we can also separate data and metadata. So we have, for example, terabytes of images, but only a handful of gigabytes of metadata describing those images.